Picture the Earth as an enormous battery, one with untold, untapped heat. The trouble? We've never been able to drill deep enough into its crust to unlock it until now. Quaise Energy, a daring MIT spin-out, is using beams of millimeter-wave energy harnessed from gyrotrons, devices born in fusion labs, to vaporize rock and carve ultra-deep boreholes. If successful, they could transform geothermal from a niche green energy into a global, constant baseload solution available nearly everywhere. Let's explore how this fusion tech drilling might just rewrite energy's future. Before we proceed to the video, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. Company background and vision: Quaise, Inc., founded in 2018 and headquartered in Cambridge, Massachusetts, emerged from MIT's Plasma Science and Fusion Center. Its founders include Carlos Araque, CEO, a former Schlumberger engineer and MIT engineer alum, and colleagues Matthew Howd and Aaron Mandel. Quaise's mission is ambitious: to drill 3 to 20 kilometers below the surface, accessing supercritical geothermal reservoirs where temperatures exceed 400 to 500 degrees Celsius, and convert existing fossil fuel power plants worldwide into clean geothermal steam hubs. They envision tapping into terawatts of carbon-free energy using gyrotron-based millimeter-wave drills retrofitted onto existing oil rigs, letting them use old infrastructure while entering a low-carbon future. Technology and development. The fusion tech core: gyrotrons and millimeter waves. Gyrotrons, massive, high-power vacuum tubes developed in the Soviet Union during the 1960s, emit millimeter waves, a slice of the electromagnetic spectrum between microwaves and infrared. These waves have traditionally been used in nuclear fusion research to heat plasma, reaching temperatures far hotter than the sun. Quaise harnesses this power to vaporize basement rock granite and basalt by directing MMWs through a waveguide, heating rock to melt and ablate it into fine glass-like ash. Hybrid drilling model. They combine conventional rotary drilling through sedimentary layers with gyrotron-powered MMW drilling once basement rock is encountered. This hybrid model enables faster, deeper penetration than standard methods that crush drill bits under heat and pressure. Standard rotary drills can go down a couple of miles, but when the rock gets too hard or hot, they switch to MMWs. Early lab tests showed only centimeters of penetration, but scaled prototypes have advanced much further. Field demonstrations and milestones. In early 2025, Quaise began yard-scale tests in Houston. MMW beams melted basalt, creating obsidian-like craters and emitting a toasted rock aroma. On June 3, 2025, they staged their first full-scale field demo atop a neighbor's oil rig outside Houston. CEO Carlos Araque called it mind-boggling, emphasizing that superhot geothermal lies just 2 to 12 miles beneath our feet, and we've finally devised a way to reach it. As of July 22, 2025, Quaise announced crossing a major threshold, drilling 100 meters into granite in the field, a breakthrough far beyond lab tests. Their roadmap: scale up to 10 times more powerful gyrotrons and build a pilot power plant by 2028. Quaise is targeting 100 megawatts thermal output by 2026, followed by the full conversion of fossil-fired power plants to geothermal steam by 2028. Why it matters. Unlocking universal geothermal potential. Today, geothermal contributes under 1% of U.S. electricity, largely confined to volcanic regions where heat lies close to the surface. Quaise's groundbreaking drilling technology changes that equation entirely, making it possible to tap into heat sources almost anywhere on the planet. Beneath virtually every spot on Earth lies a super hot zone at sufficient depth, an untapped powerhouse of clean energy. This means geothermal could go from a niche resource to a truly universal baseload energy solution. Baseload: low footprint, low carbon. Supercritical water heated beyond 400 degrees Celsius carries between 5 and 10 times more energy than conventional steam. This allows for high-density power generation from compact sites, drastically reducing the land required. Geothermal energy also operates 24/7, unlike intermittent sources like solar or wind, and its infrastructure requires less than 1% of the land and materials used by other renewables. This makes it not only scalable, but also equitable, bringing reliable power without competing for vast tracts of land. Energy independence and repurposing. Perhaps one of the most exciting aspects of Quaise's vision is its ability to repurpose existing fossil fuel power plants. Instead of tearing down infrastructure and losing thousands of skilled jobs, these plants could be retrofitted with geothermal wells. The same turbines, the same transmission lines, and even the same workforce could be repowered with endless steam instead of coal or gas. This approach dramatically accelerates decarbonization while lowering costs and minimizing disruption, giving nations a pathway to energy independence that is both fast and fair. While promising, significant challenges remain. Scaling from 100 meters to multi-kilometer depths, even tens of kilometers, is massively complex. The durability, cost, and supply chains for multi-megawatt gyrotrons are unproven. Quaise needs to raise substantial capital. $200 million is targeted to fund pilot wells and gyrotron development by 2025 to 2026. They will also require partnerships with oil majors, regulators, and utility operators to scale toward multi-gigawatt output by mid-decade. Field reliability, borehole stability, and long-term operational integrity under extreme heat remain unanswered questions. Still, Quaise is advancing faster than most expected. If gyro drilling proves feasible in real-world wells, we could see pilot plants by 2028, and repowered fossil plants providing clean steam in the years following. Has fusion tech just changed geothermal energy forever? Quaise Energy may very well be writing that narrative, with gyrotron beams turning bedrock into opportunities. By merging high-power MMW drilling, existing infrastructure, and the supercritical heat buried beneath us, they're crafting a path toward universal, always-on, affordable, clean power. The road is steep and the engineering monumental, but if they hold to their timeline, pilot wells by 2026, commercial scale by 2028, we could be witnessing the dawn of geothermal as a true backbone of global energy. Earth's heat is infinite. Quaise is aiming to make it accessible. If you enjoyed what you saw, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. Your support means a lot to us. Take care until the next one, and feel free to drop a comment sharing your thoughts. See you soon.